Last time we left off talking about different ways that calculus and pre-calculus can be used to solve problems, and the basic overall idea was we're solving problems that have more variety in them. Everything's very rigid when we're doing things with pre-calculus. Certain shapes, not all shapes, things like that. And so in calculus we're able to do a lot more because we have the ability to be more flexible, more variety. The first thing I want us to take a look at today is the two different types of problems that we're going to look at, some classic examples of where calculus is used. The first one is called the tangent line problem. So we talked about last time the tangent lines are these lines that sort of just touch curves. They don't cut through them. And so I want to talk about sort of how you can see the difference between pre-calculus and calculus in this very specific kind of problem. So in pre-calc, we can find the slope of a secant line. We can use 2 points on the curve and calculate the slope formula, right? y2 minus y1 over x2 minus x1. So the picture sort of what we're doing I'm not sure that I really need the axis drawn in there, but it's not hurting anything, is that we find these 2 points. Maybe we find the point here and a point here, and we connect them with a line like this, and we use this point, actually I'll just write it up here, as x1, y1, and this point as x2, y2, or we could reverse those, and we can calculate their slope. So that's pre-calculus. So what happens in calculus? Well, in calculus, we can find the slope of a tangent line. We do this, or we can approximate this, by using secant lines. Where the 2 points get very close together. Okay, so what does that look like? Well, I'm going to try to create sort of the same picture I just did on the other side. We're going to select those same 2 points, roughly, and we're going to find the line between them. Not exactly what I had before, but close. And basically what we're going to do is we're going to let these points get closer together. So I'm going to sort of half the distance. Maybe the half the distance is about there, and then we draw the secant line here. And then we half the distance again. So maybe the next half distance is about right here, and we draw the line here. And what happens is as these lines get, or these points get closer and closer together, these secant lines get infinitely close to the tangent line, and we're able through this limiting process to be able to find, or to approximate with precalculus, this process, to find the slope of the tangent line. And then with calculus, we're able to actually find the slope exactly. Right, the next one is called the area, or we're going to call it the area problem. Another issue or another thing that we can find with precalculus is area. So in particular, in precalc, we can find the area of certain shapes. Right, like circles, rectangles, etc. It's very specific shapes though, right? When we do this, or we use formulas, most of which, that is, the formulas mostly, come from or are based on the area of a rectangle. Which of course you'll remember is length times width. So what do we do in calculus? Well, in calculus, we can use the area of a rectangle to find the area under a curve. Notice that's an arbitrary curve, not something specific. That's the difference. Then I'm sorry, didn't want to say it that way. This is done by letting the number of rectangles become larger. Okay, so what does that look like? Well, let me draw you a picture. So let's say we have the same kind of a curve we had before. I'll draw it right here just so I have some space to work. And we want to find the area from here to here. All right, so this is from, say, A to B. What do? Well, we kind of subdivide it. We divide it in half. We can divide it in half again, and we can keep dividing it in half and making these shapes that sort of look almost like rectangles. Of course, there comes a discussion of what's the height. Do you use, what point of height do you use? I'll just use the left-hand height, like this. But you could use the right hand or a midpoint or something like that. We talk more about this when we get to this particular topic. And you'll notice that, of course, the area that you're getting in here, it isn't perfectly underneath the area or underneath the curve. But it's an approximation, and the approximation gets better and better the more rectangles you have, because the error you're getting is getting smaller and smaller. And so using calculus, we're actually able to find this area exactly instead of doing this, which is an approximation for it. All right, so what I want to do next is I want to do a couple of examples that talk about how we can find solutions either using precalculus or recognizing that precalculus is insufficient and using precalculus to at least approximate our solution. So the first one tells us that we're going to consider the equation of this curve, f of x equals 4x plus 3, and it wants to know what the slope is at x equals 2. So what you have to recognize on this is that the equation f of x equals 4x plus 3 is a line. And in a line, this location right here where our 4 is the slope. So because a line has a constant slope, that is, this line's slope is always 4, then the slope at the point x equals 2 is also 4. It's precalculus, right? I've got a line, constant slope. The difference is on this problem, I don't have a constant slope. Nope, on this problem I actually have a parabola, and its slope changes like all the time. So it's highly unhelpful on this one to kind of think about the problem in general. We have to very specifically look at the point x equal to 2. So we're going to do this with a numerical approximation. A graphical approximation is also not so very helpful for this because it's not the location that we want, it's the slope we want, and you can't sort of trace and find slope or something like that. So what we're going to do is we're going to do some approximations from the left and from the right hand side of x equal to 2. So these are my 3 points that are getting infinitely closer, not infinitely closer, but closer, incrementally closer to x equal to 2. And what I want first is I want to find the y value. So I'm going to plug these in my calculator one at a time. I'm going to find out that this is 10.63, 11.8603, and 11.98603. I'm going to do the same thing from the right hand side. I'm going to choose 2.1, 2.01, and 2.001 and find their outputs, their y values. This is 13.43, 12.1403, and 12.014003. Now, I don't really want y values. You'll notice all these y values are very close together, and they're very close to what you actually get when you plug in 2, and that's actually something else we're going to need. So let me plug in 2 up here, and when I plug in 2 here, right, I get 12. So all of these values are sort of getting close to 12 as they get closer and closer to x equal to 2. That's not happenstance, right? I mean, this is a parabola, it's a smooth curve. But we do want to find the slope, not really just the x value, or not the y value, which we know, it's 12, so we need to figure out something different than that. So what's next? Well, we need that formula for slope. So that's y2 minus y1 over x2 minus x1. And what you'll notice in this is that our focus is around the point at x equals to 2. So one of our ordered pairs is always going to be 2, 12. And I'll just let it be our second one. So this will be a y value minus 12 over an x value minus 2. And it'll be the same thing every time. And we'll do these one at a time. So the first one we're going to enter in our calculator, we're just going to go in order, is the first one that's listed here. So in your calculator, it's going to look like you're going to start with a parenthesis, 10.63, and just for the sake of being able to do this sort of quickly later, I'm going to enter some zeros. And I'm going to enter 4 zeros because none of my y values have any more than 6 decimal places, so this will work. And then minus 12, and do division. And then I'm going to do the x value, that was that one, which was 1.9. And again, all my x values have a maximum of 3 decimal places, so I'm going to put 2 zeros here, minus 2. If I put this in my calculator, calculate, I'm going to end up finding the slope is 14.3. From the regular screen in your calculator, if you hit second enter, it will pull up this previous line of text, the one that we just typed in, 10.63000 and so forth. And you can just change the 10.63 to 11.8603. And you can change the 1.9 to the 1.99. You can keep doing this process to fill in the rest of your table with those correct values. So the values, oh, I'm sorry, that was not 14.3. I wrote the wrong down. It was 13.7. Those values I'm going to fill in for us, and then we're going to take a look at what's going on with them. So if I keep plugging these into the calculator, I get 13.7, 13.97, and then 13.997. You'll notice these are getting awfully close to the number 14, right? On the other side, I have 14.1, 14.01, and 14.001, again getting awfully close to the value 14. So the answer to our question for this is, it said, if it's calculus, explain why. So why is it that we have to use calculus here? And the answer is because it's not a line. Or you could say something like, because the slope isn't constant. And it's not a constant because it's not a line. You know, in addition to that, then the question is, what is the answer? Well, we're approximating that our slope is 14. Now, we actually are correct. It is really 14. It's not just we got lucky or something like that. It really is 14. But our best statement we can make at this point is to say that it's approximately 14.